Okay, welcome to lecture 16 for ECE 203. In this lecture we're going to go over the same example that we saw in the end of the last video lecture, and we're also going to talk just a little bit about the implications of being a linear time invariant system or a linear time invariant filter, and we'll see why these are important and look at the convolution example that we actually saw at the end of the last lecture. And then we'll also just talk really briefly about a few properties of convolution and linear time invariant systems. Okay, so if we find out that a filter is LTI, okay, it's linear and time invariant, why is that important? Well, the first one is many signal processing tasks can actually be accomplished using LTI systems, right? And then more importantly, kind of what we'll focus on in the rest of this lecture and the next lecture is that we can describe an LTI system by how it affects signals at different frequencies. Okay, this is sometimes called the frequency response of the filter, and the last property is that it's just completely characterized by the impulse response. Okay, so if we have the impulse response, we know everything about the filter. All right. And so let me just state this as fact, but for any LTI system, the output can be calculated just by convolving the impulse response of the filter, right? Where that's all we do is we input a filter, or excuse me, input an impulse into the filter, and that gives us h of n, and then we convolve that with x of n, the input signal, right? And kind of a longhand representation of what's actually going on is written right here. Right? All right, so let's see an example of that. How would we do this? Well, the example we're going to look at, and it's the example we've seen in the last lecture, was a digital differentiator. So this is really going to be no different than the last example, but we'll run through it quickly in this lecture. Okay, so the relationship between the input and output is given by y of n. So the output at time n, that's just equal to 1/2 the input at time xn minus 1/2 times the input at x of n minus 1. So what's the impulse response, right? All we do is we replace the x of n with the input delta of n, and that gives us the following relationship. The impulse response, h of n, equals what's written there. And of course we can just plot that. That's plotted right here. Right? That's what h of n looks like. So how do we calculate the output when the input is given by this signal x of n, which I've drawn on the screen right here. It's drawn in blue. All we do is we go back to our original equation, and then we're going to just kind of tease this apart. Okay? And so we would write the output y of n, like I said, is the convolution, and then in kind of the long notation of what's really going on is written right there. So how do we compute that? Let's see on the next slide. So again, I've just drawn this on the top of the screen. We have h of n, the impulse response, convolved with the signal x of n. That's the idea of what we're doing. And so we'd start and just say, I'm going to compute the value at y of 0, right? And so if we look at that equation, the equation written right here, we're just going to plug in n equals 0, right? We're going to plug in n equals 0 right there. And when we do that, then we're multiplying h of k times x of 0 minus k, right? And x of 0 minus k, that's just x of k. So now let's plot those two things. The first thing we're plotting is h of k. That's just the impulse response. That looks exactly the same, right? That looks, no different than h of n. Okay, so that's being plotted in red here. Okay, that's h of k. And then the next thing we're going to plot is x of minus k. And now we're plotting x of minus k because that was given to us in this equation up here, right? So plotting x of minus k, the effect that has is that flips the signal, right? It flips the signal around the origin. If we were evaluating, say, x of plus 7, then we'd be really evaluating x of minus 7. And so that has this effect that it flips things. Example here would be, or say, if we want to find out on this plot, what is the value when k equals 2? Well, that should be x of minus 2, right? Okay, so that's the idea of how we flip this in this signal in time. And now what the equation up here is telling us to do is it's saying after you've flipped the signal and after you've drawn the impulse response, multiply and sum over all values of k. So that's exactly what we're going to do. We're going to multiply these two signals together, and you can see in all these locations where h of k is 0, when that gets multiplied by x of k, that's just going to kill off all those values of x of minus k. So the only place where it's non-zero is when k equals 0, right? We have kind of this value multiplied by this value, and what does that give us? That gives us, well, this bottom value, x of minus k at 0, is minus 2, or plus 2, and the top value, h of 0, is 1/2. So we multiply those together, and we're going to sum those all up. Let's maybe see that on the next page. All right, multiply and sum. I've actually plotted here the multiplication step, h of k times x of minus k. Everything is 0 except that k equals 0. And then we're summing over all values of k, so we just take the value 1. So that gives us y of 0. All right, let's continue. Let's calculate y of 1. We're going to do the same thing. We're going to now go back to that original equation and plug in n equals plus 1, right? And when we do that, we see that somehow we've shifted this bottom signal, this blue, this input signal, x of n. That's kind of been, not only is it flipped, but now it's shifted one to the right. Okay, so h of k looks the same, right? That doesn't change. And what we're doing then is we're multiplying those two things together, and that gives us this green signal again, this signal here, and then we're summing up over all values of k. So here we have 2 minus 1. So y of 1 equals 1. All right? And then we can continue, say y of 2. Now this time we won't draw the actual multiplied signal together. Let's just draw h of k looks the same. X of 2 minus k, now we've somehow shifted things to the right from our original one. We've shifted this whole signal to the right by 2. Okay? So here we're just going to multiply and sum. We won't draw the signal again, but we now would say y of 2. There's only 2 non-zero values, and those are these ones circled in green, right? And then we get this thing, which is 6 multiplied by 1/2. That gives us 3. And this one multiplied by minus 1/2, which gives us 2. It's 4 times minus 1/2 is minus 2. Okay, so that adding all those up, we just get 3 minus 2, which is 1. And we continue in this way, keep going, and really what you'd see is y of 3 is minus 1, y of 4 is minus 1, y of 5 is minus 1, and then we'd plot y of n. Okay? And y of n would be 0 all the way up until n equals 0, and then it would take the value 1 up until 3, where it would take the value minus 1. Now it would be minus 1 for values of n, 3, n equals 3, n equals 4, and n equals 5. Okay? So this was it's a lot of work, and when we do this, it's best to only do simple examples. It's easy to kind of get mixed up a little bit. So another thing we can do is just do this in MATLAB, right? We just write convolve, and we input two vectors. We input the vector x, which contains the signal x, and h, which contains the impulse response, right? And then the last thing to remember is we write this as y of n equals x of n convolved with h of n. So intuitively, I kind of want to give an example of what's happening, or give some feeling of what's happening. So here's the input signal x of n, right? And here's the impulse response h of n. And what we're doing is we're flipping the input signal, right? There's the flipped input signal. Flipped input signal. And then we're kind of sliding it to the right, right? And we're passing it through this blue filter. What I mean by passing it through the blue filter is we're just multiplying the points that line up and adding them together. And then the output, right, is given down here. Okay? So the reason we flip the signal, one way to think of this is the input, this first value in red corresponds to x of 0, right? The second one would correspond to x of 1. And somehow this is very intuitive in that the first value of the input signal, that should be the first thing that goes into the filter, right? And the second value should be the second thing that goes into the filter. So graphically, we just think of this as flipping the signal, right? And then sliding it through, shifting it and sliding it through the impulse response of the filter. And then at every time, we're summing up the output, and that's drawn right here. Okay. So let me just remind everybody of a few things that we've seen. We've seen this fact that the output of any LTI system can be computed by convolving the impulse response of the system with the input signal. And that's just written, written again right here. But we want to note that FIR filters, they are LTI filters, or linear and time invariant. And we didn't really show that yet, but I have it written out down here. Now I don't want to step through these equations one by one, but we're just basically taking the definition of linearity, and then we're taking an arbitrary FIR filter, right? So an arbitrary FIR filter that's kind of given by this equation here, right? Remember, we're taking this sum. We had BKs written before, so this h of k, we showed that was the same as the BK, so we're putting h of k there. And that's getting convolved with the sum of two input signals. And then if you kind of methodically go through this, you show that the output is exactly the same as if we had just input the signals individually and then added them up after the fact. Okay. Time invariance, it's the same. It's a little easier to show even. But all we're doing is taking the form, this is the equation for an FIR filter, right? The output of an FIR filter. We're delaying the input by some amount. And note that when we delay that input, right, delay the input by n naught, then all that ends up doing is we can just redefine the time index, set that to be L equals n minus n naught, redefining the time index, and then plug that back into the equation, and then the output we get is just y of L, right? But the output is y of L. We knew L equals n minus n naught, so we get back time-delayed version of the input, okay? So FIR filters are linear and time invariant. And the last thing I want to mention today is a couple properties of LTI systems. Okay? And the first one is that we have this drawn up here. This is some filter, some system. We're inputting a signal x of n, goes into the filter h1. The output is y of n. Then we know this is the expression for the output. It's a convolution of the impulse response and the input. And there's a couple properties of impulse couple properties of convolution that are important that tell us something about how filters behave. And the first one is this commutative property. All I did here was I changed the order of x and h, so I can convolve x of n and h of n, and that's the same as convolving h of n and x of n, right? These are relatively easy to prove just by looking at the definition of convolution. The second property is the associative property, and that's just saying that, if we convolve, say we have three signals, if we convolve x1 with h1, and then take that new signal and convolve it with h2, that's the same as if we convolved h1 and h2 first and convolve that with a signal x of n. Right, so what does this tell us about LTI filters? It tells us the following. It just tells us that if we input a signal x of n, so I'm inputting a signal x of n here, and if that goes into a filter h1, okay, so the output kind of at this point should be, I'll write this as just shorthand h1 convolved with x, right? So this whole signal then gets convolved with h2. Right? So the output here should somehow be h2 convolved with h1 plus h1 convolved with x, right? Now let's switch the order of operations here. Let's input x of n again, but now let's input it in the filter h2 first, right? There's h2 first. Then what's the output here? It's going to be h2 convolved with x. And then what's the output here? The output should be, well, it should be h1 convolved with h2 convolved with x. So the associative property tells us that these two things are the same, right? These are the same. And that tells us that it doesn't matter the order in which we apply a filter to a signal. We can apply, if we have two filters, we can apply either one of them first, and the remaining one second, or we can swap that order and we'll get the same output. Likewise, that tells us, lastly, that if we just take the signal x of n, the same signal x of n, and input it into a filter that has the impulse response equal to h1 convolved with h2, that's also going to be the same, right? Because this output now would be, say, h1 convolved with h2 convolved with x. That's also going to be the same. So really we can combine filters, we can take them apart, provided this total effect of their impulse responses is the same, meaning that when we convolve all the impulse responses together, that they end up giving the same overall impulse response. Okay, we'll stop there.